Hello everyone. We started talking about MRP systems, and in the previous video, we just discussed a simple example about MRP calculations. In that example, we used a production plan called lot for lot. What I mean with lot for lot is that, in fact, in that plan, we make the production plan just equal to the net requirement of that period. And in this method, we do not carry any inventory, but if we have a setup cost for the production, then we have that setup cost for each of the periods. Now I will introduce you four more lot sizing methods in MRP systems. These are economic order quantity method, the silver meal heuristic method, least unit cost method, and lastly part period balancing method. And all of these methods are heuristic methods. We do not guarantee the optimal solution with these methodologies. Let's start with the first one, economic order quantity method. In fact, we just talked about EOQ models for the inventory control management part. We were determining the optimal order quantities with this model. And the aim of the EOQ model is to create a balance between the setup cost and inventory holding cost. Again, here our aim is to create this balance between setup and inventory holding cost. With the EOQ formula, we will determine our production amounts. We have three inputs for the EOQ formula. These inputs are the average demand rate lambda, the holding cost rate h, and the setup cost k. And let's again consider the previous example, the example about the trumpet production. And one of the components of the trumpet was valve casing assembly, remember that. And now we will determine the production amounts of valve casing assembly with EOQ lot sizing. And now suppose that there is a setup for producing this assembly. It says that for this setup, it takes two workers about 3 hours, and we pay $22 for the workers per hour, and that translates to a setup cost of $132. So when we plan a production, each time we have such a setup cost. And also, the company uses a holding cost based on a 22% annual interest rate. And we assume that the cost of these assemblies is approximately $141. And now we will calculate weekly holding cost by multiplying the cost of the product with the annual interest rate, but we will divide this with 52 because we want to calculate this holding cost weekly, and we obtain a holding cost of $0.6 per valve casing assembly per week. And lastly, we need an average demand rate lambda, and we check the net requirements over weeks 8 through 17, and it is 439, and we divide this with 10 to obtain the weekly demand rate, and we obtain 43.9 units per week. But in fact, here we assume that the demand is constant and continuous, because this is one of the assumptions of the EOQ model. But here in the real case, in fact, our demand is not constant and continuous. So EOQ, in fact, is not designed for a system with discrete time periods such as MRP. But now we are assuming this constant demand. So our solution, in fact, will be a heuristic. We do not guarantee the optimal solution with this methodology. Now let's calculate the EOQ value for this example. You already know this formulation, and we insert our setup cost, demand rate and holding cost into the formulation and obtain the EOQ value as 139. This is the production lot size for the example. Now in the table we see the time phase net requirements, and now we begin production at the first period with this amount that we obtained from the EOQ formula, and we see that this amount is enough to supply the demand of the next 3 periods also. So we do not plan any production for these periods, and here we again make a production plan and see that this plan is enough for the next period also. And then again we make a plan and see that it is enough to supply the net requirements of the next 2 periods. So we do not make any plan in the next 2 periods. And in the last period again we make a production plan. And since the production lead time for this assembly is 4 weeks, we have the plant deliveries 4 weeks later than the plant order release. And now we will calculate the ending inventories. Here is the formula to calculate the ending inventory. We sum the beginning inventory with plant deliveries and subtract net requirements. For example, for here, for the week 8, we do not have any beginning inventory, but we have plant deliveries with an amount of 139. We subtract the net requirement 42 from this and obtain the ending inventory as 97. And for the next period, we do not have any plant delivery, but we have beginning inventory as 97, and we subtract the net requirement 42 from 97 and obtain the ending inventory as 55. And we do the same operation for all of the periods and obtain the ending inventories. These ending inventories are important for us to calculate the total holding cost of the system. Now let's check the total cost if we apply this EOQ lot sizing. Here let's first calculate the setup cost. In the plan we see that we planned 4 different productions, so we have setup cost for each of these 4 periods. So we multiply the setup cost with 4 and obtain $528 for the setup cost. And for the holding cost, we sum all the ending inventories, and we see that we have this number multiply with the unit holding cost weekly and obtain $391.8 for the inventory holding cost. We sum the setup cost with the inventory holding cost, and the total cost of the system is $919.8. Let's check what would happen instead of using EOQ lot sizing if we use lot for lot. In lot for lot, we don't carry any inventory, so we don't have any inventory holding cost. But since we have production in each of the periods, we have setup cost for each of the 10 periods. So the total cost is $1,320. So we see that there is an improvement in the total cost when we used EOQ lot sizing model. But by the way, this doesn't guarantee the improvement in the whole system, because we applied this EOQ lot sizing here only for valve casing assembly and calculated the total cost for valve casing assembly. But when we apply this EOQ model to valve casing assembly, in fact, we automatically apply it to the components in the second level, I mean slide assemblies and valves. Now let me show you the MRP calculations for valves. Okay, here you know 3 valves are required for each valve casing assembly. So since our EOQ lot sizing was 139, we multiply this with 3 and obtain the lot sizing for the valves as 417. And here is the production plan for the valves. But maybe when we calculate the total cost for the valves, there may not be an improvement. Here the improvement is only for the valve casing assemblies. Now I will introduce you a new heuristic for determining the lot sizes. It is called silver meal heuristic. You know, in the EOQ model, the aim is to make a balance between setup cost and the inventory holding cost. Again, in this method, our aim is to create a balance between setup cost and inventory holding cost. Now, assume that T is our periods and CT is the average holding and setup cost per period if the current order spans the next T periods. For example, C1 means that we are at period 1 and we are making our production plan only for that period. So we only have a setup cost of K. And C2 means that we are at period 1 and we are making our production plan for period 1 and the next period. So we have a setup cost and we have a holding cost, and we sum these, divide with 2 since we have 2 periods, because this T values shows the average holding and setup cost. And for C3 again we have a setup cost and we have holding cost. We sum them up and divide with 3. And according to this methodology, each time we check Cj with the previous Cj. If Cj is higher than the previous Cj, then we stop and we make that production plan. And again we make the same operations for the rest of the periods. Now I will show you an example about this heuristic, and probably it will be more clear to you. Now, according to this example, we have 5 periods, and here the demand is given for these 5 periods. I mean, these are the net requirements for each of these periods. Holding cost is $2. We are producing cases. Holding cost is $2 per case per week, and production setup cost is $80. Now, first we calculate C1. So we assume that we are making the production only for the first period. So we only have a setup cost of $80. And for C2, we assume that we are producing the net requirement of the first period and the second period in the first period. So we have a setup cost, but we also have an inventory holding cost because we carry the inventory of 30 units for 1 week, and we sum the setup and the inventory holding cost, divide with 2 to find the cost per period. It is 70. And I check if it is greater than or less than the C value of the previous period. It is less than, so I continue my calculations and I calculate C3. Now I am making the production of the first period, second period and third period. I have a setup cost, I have inventory holding cost, and I divide it with 3 to find the average cost, and it is 102. So it is higher than 70, so I stop because C3 is greater than C2. So I make my production plan for the first 2 periods. Then I come to third period and I start at that period again, make the same calculations. I mean, at the third period, I calculate C1 assuming that I am only producing the net requirement for third period. So I have only setup cost. Then I calculate C2 and I obtain 45. It is less than C1. So I continue calculating C3, but I obtain a higher value in C3 when I compare it with C2. So I stop. Now in this case, I decide to make a production in third period for 2 periods. And since I only have the last period, I make the production plan in that period for the net requirement of that period. So here is my production plan. In the first period, I produce 48. In the second period, I don't make production. In the third period, I produce 47. In the fourth period, I don't make production. And in the last period, I make a production of 20. This is the solution that I obtain when I apply Silvermeal heuristic approach. Now I will introduce you a new method called least unit cost method for lot sizing. This method, in fact, is similar to the method that we just discussed, I mean Silvermeal method. You know, in the Silvermeal method, we calculate the total setup and inventory holding cost and divide with the number of periods to find the average cost per period. But now we again sum the setup and the inventory holding cost, but divide with the number of units demanded through those periods. So we find the average cost per unit. Now let me show you an example. We have the same example that we used in the Silvermeal method. Here we calculate C1. We divide it with the number of units required for period 1 and obtain 4.44. For C2, we calculate the total cost, divide with the net requirement of period 1 and period 2 and obtain 2.92. It is less than previous C value. So I continue calculating C3. And at C3 I obtain 3.42, which is higher than previous C value. So I stop here. So I make a production plan for the first 2 periods in the first period. Now I am at period 3. So I start making the same calculations. I calculate C1, obtain 1.9. I calculate C2, obtain 1.92. It is higher than previous C value. So I stop here. So I make a production plan only for period 3. And now I am at period 4 and I make the same calculations. I calculate C1 16. I calculate C2 as 4.8. It is less than the previous C value. So now I make a production plan for 2 periods. I mean, I produce the requirement of the 5th period in the 4th period. So here is our production plan 48, 0, 42, 25 and 0. With this production plan, we obtain a total cost of $340 for the setup and inventory holding cost. But when we check the total cost that we obtain with the Silvermeal method, we see that it is $310. So it is less than this number. So for this example, we can say that Silvermeal method performs better. And lastly, for these heuristic methods, I will introduce you part period balancing method. In this method, we set the order horizon equal to the number of periods that most closely matches the total holding cost with the setup cost over that period. Let me show you an example. In fact, we will use the same example that we used for the previous methods. Here, for the horizons, we calculate total holding cost For the first horizon, since we don't have any holding cost, it is 0. If we make a production plan for 2 horizons, we have a holding cost of 60. And if we make a production plan for 3 periods, we have a holding cost of 228. We see that this 228 is more than our setup cost 80, so we stop and we check which one, 228 or 60 is closer to our setup cost 80, and we see that 60 is closer. So in fact, we make a production plan for 2 periods. And we come to the third period and we again make the same calculations. We calculate the total holding cost for if we make a plan for 1 period 0, then 2 periods it is 10, then 3 periods it is 90. Here we see that 90 we exceeded our setup cost 80, so we stop and we check if 10 is closer to 80 or 90 is closer to 80, and we see that 90 is closer to 80. So we decide to make a production plan for 3 periods. So in fact, in the end, we have such a production plan 48, 0, 67, 0, 0. And we obtain a total setup and holding cost of $310 with this method. In fact, this cost is same with the cost that we obtained with the silver meal method, but the solutions were different. In fact, these are optimal solutions. Even though these are heuristic methods, even they do not guarantee optimal solutions. Sometimes it is possible to obtain optimal solutions, but with 2 different solutions, we obtained the same objective function, same total cost. So in fact, these are alternative optimal solutions. As I mentioned, the methods that we discussed are all heuristic methods. They do not guarantee optimal solutions. Now I will introduce you Wagner-Witten algorithm. This is an algorithm for determining lot sizes for production plans, and it gives the optimal solution to us. I will explain this method with an example. In this example, we have 4 periods, and these are the net requirements for each of these periods. We have a holding cost of $1 per unit per period, and we have a $75 of setup cost. Here in this method, in the Wagner-Witten algorithm, we create such a network. We have 4 periods, we have nodes for each of these periods, and we have a dummy node. This shows the end of these periods, and our aim is to go from the first node to the 5th node. You see there are different paths on this network. We can use, for example, this path to go from 1 to 5, or we can use this path to go from 1 to 5. What we mean with these different paths? For example, if we go from 1 to 5 directly with this path, it means that at period 1 we make production plan for all the periods, and we carry inventory, of course. For example, if we use this path, for example, if we go from 1 to 3, it means that we make a production plan in the first period for 2 periods, for 1 and 2, and then come to the third period, and in the third period we make a production plan for the periods 3 and 4, and we go to the end. So now our aim is to find the path with the least cost. So we have to calculate the cost of these arcs. Firstly, what we have to do is to calculate the cost of these arcs. We calculate the cost, then our aim is to find the shortest path from 1 to 5. We can solve an optimization model to find the shortest path from 1 to 5, Or since this is a very small example, it is possible to calculate the cost of all the paths as given in this table, and we can check which path has the least cost. And when we check this table, we see that 1, 2, 4, 5 has the least cost with $248. What we mean with this path, let's check it. We go from 1 to 2, it means that we make a production plan in period 1 for only that period. And we go from 2 to 4, so we make a production plan in second period for periods 2 and 3. And in the fourth period, we make a production plan for the fourth period. And we obtain the least setup and inventory holding cost with this plan. This is the optimal policy for this problem. Now I will talk about incorporating lot sizing algorithms into the explosion calculus. Now let's return to our example about the Harman Music Company, the company that produces trumpets. Now we will consider the impact of lot sizing on the explosion calculus. Firstly, let's consider valve casing assembly. These are the time-phase net requirements for this assembly. We assume that there is a setup cost of $132 and holding cost of $0.6 per assembly per week. Now we will apply Silvermeal heuristic approach for this assembly, and when we make the calculations, we obtain such a production plan for this assembly. Here you see the plant order release, and you see the plant deliveries since the production lead time is 4 weeks, and we calculate the ending inventories, and we calculate the total cost, total setup and inventory holding cost, and we obtain $650.4 with this methodology. And the total cost when we used lot for lot production plan was $1,320, and when we used EOQ model, it was $919.8. So we see that there is a really good improvement in the total cost when we use Silvermeal methodology. Now, we solved the same example with Wagner-Witten algorithm. The algorithm which gives us the optimal solution. And according to this solution, the total cost is $610.2. You see that this cost is really close to the cost that we obtain with Silvermeal methodology. So we see that this heuristic approach is an effective approach for this problem. Now we applied this method for the let me show you, for the valve casing assembly, a component in the first level. Now this production plan will also affect the production plan of the components in the second level. Let's consider the production plan of the valves now. When we apply the Silvermeal method for valve casing, let me show you, we will have these net requirements for the valves. And here I will show you the plant order release when we apply Silvermeal methodology, and you can see that in fact the numbers are exactly same as the numbers in net requirements. In fact, even we now apply the Silvermeal methodology, we obtain a solution that we obtain with the lot for lot methodology. So now we see the effect of this heuristic approach in the explosion process. Even we applied the Silvermeal methodology, in the second level, we obtain a solution that we obtain with the lot for lot methodology. Now I would like to talk about lot sizing with capacity constraints. You know, in the previous examples, we didn't consider the capacity constraints, but in real life, we always have capacity constraints. I mean, for each period, we have a maximum amount of production that we can do in real life. When we consider capacity constraints, in fact, we make our problem more complex, and determining true optimal policies is difficult and time-consuming and is probably not practical for most real problems. Now I will show you some examples. For example, we have 4 periods, and these are the requirements for these periods, and the capacity of each period is 60. Firstly, let's calculate the total requirements of these 4 periods. We see that it is 218, and the total capacity of these 4 periods is 240. Since the total requirement is less than the total capacity, firstly we can think that, okay, we can find a feasible solution for this problem. But in fact, there is no feasible solution for this problem, because the total requirement of the first 2 periods is more than 120. I mean, total capacity of the first 2 periods. So it is impossible to satisfy the demand of the second period. So there is no feasible solution for this problem. So firstly, we should check if we can find a feasible solution or not. To be able to check this, what we do is that, firstly, we calculate the total requirement for 1 period, for 2 periods, for 3 periods, for 4 periods, etc. Also, we calculate the total capacity for 1 period, for 2 period, for 3 period, and we continue to the end. And we check if the total requirements are less than the total capacities or not. If they are always less than, then we can guarantee that we can find a feasible solution for that problem. Now, when I check, I see that all these requirements are less than the capacities, so I can say that I can find a feasible solution for this problem. Now let's find a feasible solution for this problem. Okay. Firstly, I check when I firstly exceed the capacity. I mean, the requirement exceeds the capacity. Here in the first period, the requirement is less than the capacity. In the second, it is again less. But in the third period, the requirement is more than the capacity. So what I have to do is that I have to backshift some part of this requirement to the previous periods. So for the third period, I can say that, okay, I can produce 60 units, but I have to shift 40 units of this requirement to the previous periods. So I have to shift 40 units to the second and the first period. I check the second period. Now I see that I have an excess capacity of 20 units here. So I can shift the 20 units of the third period to the second period. But I still have to shift 20 units. So I shift these 20 units to the first period and make the production amount 40. Now again I continue. For the fourth period, the requirement is less than the capacity, but for the fifth period, I see that the capacity, the requirement exceeds the capacity. So I can say that, okay, I can produce 60 at this period, and I have to shift 20 units to the previous periods. So I see that there's enough capacity in the previous period. So I shift these 20 units to the previous period and make the production amount 55 here. Okay. And lastly, here you see that the requirements exceed the capacity. So I have to shift this 15 units to backwards. So I check the previous period, the capacity is full. I checked again this period, I have an excess capacity of 5 units. So I increase the production plan from 55 to 60. But I still have to shift 10 units. So I check the other periods. Here the capacity is full, here the capacity is full. So I shift this 10 units to the first period and increase the production plan from 40 to 50. And lastly, I obtain such a production plan that I satisfy the requirements and also I satisfy the capacity constraints. But this is only a feasible solution. I mean, there may be other solutions that are better than this solution. So at this point, I will try to improve my feasible solution. In the improvement step, I will check if there is any lots that I can remove. I mean, if I can eliminate a lot, a production plan in a period and produce it earlier, then I will not have a setup cost in that period, but I will have an inventory holding cost. But if this inventory holding cost is less than that setup cost, then it would be better to shift backwards some of the lots. Now I will show you an example how we do this. For example, in this example, we have this requirement and these are the capacities. We have a setup cost of $450 and holding cost of $2. And as I showed you, we can find a feasible solution for such a problem. And here we have an initial feasible solution. Now our aim is if it is possible to improve this feasible solution or not. Firstly, let's calculate the cost of this initial solution. For the setup cost, we have $4,050, and for the inventory holding cost, we have $432. Now, we have such a table. We calculate the excess capacities for each of the periods. We start from the last period. Okay, we have a production plan of 30 units in this period. And we check if we can shift backwards this lot. When I check the previous periods, I see that there are no excess capacities in these periods. So I can shift this lot to the fifth period because there is an excess capacity in the fifth period. Now, if I shift this lot 4 periods earlier, then I will have an inventory holding cost of 30 units multiplied with 4 periods multiplied with $2 and $240. And as I mentioned, the setup cost is $450. So this holding cost is less than the setup cost. So I decided that it would be better to shift this lot to fifth period. Now I check the production plan in week 8. We have to produce 50 units. And now I will check if it is possible to produce these 50 units in the previous periods. When I check the previous 2 periods, I see that there is no excess capacity. But here in the 5th period, still we have an excess capacity to produce these 50 units. So if I shift this production plan to week 5, then I have to hold inventory for 3 periods, and this makes a $300 inventory holding cost. And since this is less than the setup cost of $450, then it would be better to remove this plan in week 8 and shift this plan to week 5. And this is the updated table. I update the amount of production in week 5, and also I update the excess capacity in week 5. I continue. Now I will check the production plan in week 7. I have to produce 120 units, and I check that I still have excess capacity to produce this amount in week 5. So I will check if it would be possible to produce this amount in week 5. When I calculate the holding cost, I see that the holding cost is $480, and this exceeds the setup cost of $450. So it is not reasonable to shift this plan to previous period, week 5. So now I decide that, okay, let's keep this production lot in its period. And I come to 6th period. Here I have to produce 50 units, and I will check if I can produce it in week 5. When I check the holding cost, I see that it is less than the setup cost of $450. So I decide to shift this production plan to the previous period. And I update the table in this way. Now I still continue checking if I can shift any of the lots to the previous periods. Now I see that there is also excess capacity in week 4. So I may try to shift all the production in week 5 to week 4. So I will check if the inventory holding cost is less than the setup cost or not. Okay, when I shift this production amount to week 4, I will have an inventory holding cost of $316, and this is less than our setup cost. So I decide that it would be better to shift this production plan to the previous period. And now again I check if there is any lot that I can shift backwards, and I see that there is no lot. So this is our plan. This is our final plan. Here is our final plan, and these are our requirements. And when we calculate the setup cost, we see that it is $2,250, and we calculate the inventory holding cost and obtain $1,388 with a total cost of $3,638. And the total cost of the initial solution was $4,482. So we see that there is an improvement of 20%. I mean, after finding the feasible solution, we can improve that feasible solution by shifting the lots to backwards. Okay, that's all that I would like to talk about MRP systems. Thank you for listening to me. See you next week.